Hi, in this video we are going to see the symmetry property of the Fourier transform. Now what do we mean by this property? Again, we have a Fourier transform pair, x of t and x of omega. The symmetry property tells us the following. Fourier transform of the conjugate, complex conjugate of x of t is x of minus omega complex conjugate. Okay, here star denotes complex conjugate, conjugation. Sometimes this can be also denoted as x of t bar, again meaning conjugate, x of minus omega bar. Okay, here bar also means complex conjugate. So both of these notations are encountered in the literature. Okay, proof of this statement is quite easy, as follows. Fourier transform of x conjugate of t, complex conjugate of x of t, Fourier transform of this function x conjugate of t e to minus j omega t. By using the Fourier integral, we can evaluate the Fourier transform by means of this expression. Now we can write this integral in the following way. We can write this as x of t e to j omega t dt conjugate. Because the complex conjugate of the integral can be reduced to the integral of the complex conjugate of the integrand, and the complex conjugate of e to j omega t is e to minus j omega t. And we can furthermore write this as from minus infinity to plus infinity x of t e to minus j minus omega t integrated with respect to t, complex conjugate, but we recognize this as the expression here is just the Fourier transform evaluated at minus omega. So the Fourier transform of the complex conjugate of x of t is the Fourier transform of x of t evaluated at minus omega, and then we take the complex conjugate. Okay, now we have this result. Now, a very important conclusion related to this result is the following. If x of t is real valued, then we know that x of t will be equal to x conjugate of t. Meaning that if you evaluate the Fourier transforms of x of t and x conjugate of t, x of omega will be equal to x of minus omega complex conjugate. Or we can write this in the following form: x of minus omega is equal to x conjugate of omega. Now, for real valued signals, this relationship is satisfied by the Fourier transform, which is an important result because it tells us the following. For real valued signals, it is sufficient to know the Fourier transform for positive frequencies, because you can obtain the Fourier transform expression for negative frequencies by using this expression. Another interpretation of this result is as follows. In the Fourier transform of real valued signals, whatever you have at positive frequencies, whatever expression you have at positive frequencies, there is a counterpart of that expression at negative frequencies. So this also explains the usage of the negative frequency concept in the Fourier transform. So negative frequencies are essential to describe the Fourier transform of real valued signals. Okay. So for real valued signals, we have this important result. Now we can use this expression to obtain some results related to the real and imaginary parts of x of omega, and also the magnitude and the phase of x of omega. Now, x of omega, remember, can be written in rectangular form as the real part of x of omega plus j, imaginary part of x of omega. Now, let us call this equation star, or equation 1, let us say, because star now denotes conjugation 1. By equation 1, we can write this expression in terms of the real and imaginary parts as follows. xr of minus omega plus j times xi of minus omega is equal to xr of omega minus j xi of omega, because we have conjugation. So we obtain the following results. xr of minus omega is equal to xr of omega. So this is therefore even function of omega. So for real valued signals, the real part of the Fourier transform is an even function of omega, and similarly xi of minus omega is equal to minus xi of omega, meaning that it is an odd function of omega. Okay. Now also we know that x of omega can be written in polar form as magnitude or modulus of x of omega e to j phase of x of omega. So again, by equation 1, we have a magnitude of x of minus omega e to j phase of x of minus omega. So this is x of minus omega is equal to magnitude of x of omega e to minus j phase of x of omega. This minus sign is coming from complex conjugation. Therefore, we see that magnitude of x of minus omega is equal to magnitude of x of omega, implying that magnitude of x of omega is an even function of omega, and phase of x of minus omega is equal to phase of x of omega, implying that phase of x of omega is sorry, we have a minus sign here, is odd. Okay, so if we summarize these results for real value signals, the Fourier transform of the real value signal satisfies the property given by equation 1, meaning that the real part of the Fourier transform turns out to be an even function of omega. Odd part of the Fourier transform, imaginary part of the Fourier transform turns out to be an odd function of omega, and magnitude of the Fourier transform is again even, and phase of the Fourier transform is odd as functions of omega. Thanks for watching.